In general, there are two main types of titration that you will normally see. A weak acid and its conjugate base, and you will add a strong base to it. Number 2 is a weak base and its conjugate acid, and you will add a strong acid to it. So this first example we are doing is a titration of 40 milliliter of 0.2 molar hypochlorous acid by 0.1 molar KOH. Calculate the pH after the following volumes of KOH is added. The Ka is provided for the hypochlorous acid, so this is a weak acid plus a conjugate base. In part A, no strong acid is added, so this is just a regular ice table. Since Ka is provided, we're going to take the acid and dissociate into its ion. Remember, weak acids do not dissociate completely. This is why we do an ice table. The acid here is hypochlorous acid, so HClOAQ will dissociate into H plus AQ plus ClO minus AQ. And since no strong base was added, it is just a regular ice table. We started with 0.200 molars of HClO3. We have no H plus and no ClO minus. Minus X on the reactants plus X on the products. Equilibrium is the addition of IC, so 0.200 molar minus X, X, and X. So my Ka is products of a reactant, which is H plus times ClO minus over HClO. Plugging in the numbers for the equilibrium value, that's going to be X times X over 0.200 molar minus X. The Ka given for HClO is 2.9 times 10 to the negative 8th. I'm going to assume the 5% rule, and I could do that because my Ka is so small, hypochlorous acid does not really want to dissociate. So my X equals to 7.6 times 10 to the negative 5th molar. That is the concentration of my H plus at equilibrium. So pH is equal to negative log of H plus, which is negative log of 7.6 times 10 to the negative 5th molar, which equals to 4.12 with correct sig figs. So if you don't think that we could do the 5% rule, you could always double check using the 5% formula, which is percent is equal to the concentration of X over the acid's concentration times 100. This is going to be 7.6 times 10 to the negative 5th molar divided by 0.200 molar times 100. This is equal to 0.038%, which is less than the 5% rule, so the 5% rule is valid. In this problem, you really didn't have to check because my exponent is to the power of negative 8 for Ka. That means the acid does not really want to dissociate. In part B, 10 ml of the strong base is added. Started with a weak acid and a strong base is added. We need to do a BCA table, figure out how much of the weak acid is neutralized by the strong base. So the first thing we need to do is convert our molarity into moles, because the BCA table must be calculated in moles to figure out how many moles of the base and how many moles of the acid are completely neutralized. For the acid, we started with 40 milliliters. Using dimension analysis, we need to convert the milliliters into liters, 1 liter to 1,000. 1 liter has 0.200 moles of HClO. This is equal to 0.00800 moles of the acid. For the base, we have 10 milliliters. I'm going to convert the milliliters to a liter, and 1 liter has 0.100 moles of KOH. This is equal to 0.00100 moles of KOH. Since we are doing before and after, we need to write acid-base neutralization. The acid is HClO plus the base, which is KOH. This is going to yield a salt KClO plus H2O. Your HClO is your acid. This is your base. This is your salt. And this is your water. This is a double replacement reaction, so the H and the K replaced each other. KOH is a strong base, so that's going to be a K plus and an OH minus. And potassium is usually soluble, so that's K plus ClO minus. The K's cancel out, so the equation is actually HClO plus OH minus ClO minus plus H2O. And now we're going to do the BCA table. The before concentration must be in moles to account for the neutralization. We calculated those values above. HClO moles are 0.00800 moles. The OH minus is going to be 0.00100 moles, because for 1K there's 1 OH minus. ClO minus is 0. The water does not count because it's not part of the equilibrium equation. So if I look at this, my limit is going to be my OH minus because I have the least amount. So on the reactant side, I am going to subtract by 0.00100 mole. On the product side, I'm going to add 0.00100 mole. And to get the after, I'm going to add the 2. For the acid, is 0.00700 mole. And for OH minus, there's none. It was all used up to neutralize 0.001 mole of HClO. And the ClO minus, the conjugate base, we have 0.00100 mole. Since we have acid and the conjugate left over and we have Ka, my next step is I'm going to write an equilibrium dissociation reaction of HClO. In order to calculate the equilibrium table, it must be in molarity. So the first thing I'm going to do is calculate the new molarity because the volume is additive now. Molarity is equal to moles over volume. So the molarity of HClO, this is the new one, is going to be 0.007 because this is the current that I have left over divided by the total volume, which is 40 ml plus 10 ml. Need to convert milliliters into liters. This equals 0.140 molar. And you need to find a new concentration of the conjugate base, which is ClO minus. That is 0.00100 moles over 40 milliliters plus 10 milliliters converted into liters. This equals to 0.0200 molars. So the ice table, we're going to use the acid because that is what is present, left over. It's going to dissociate down to H plus ClO minus. These are all AQs. And the ice table must be in molars. So the HClO is 0.140 molar, and we use this because some of the HClO was neutralized by the added base. The H plus, we still have nothing. ClO minus, we have 0.0200 molar, and we do the regular ice table. The E is the addition of IC, so that is 0.140 minus X 0.0200 molar plus X. So Now I write my Ka. Ka is going to be products of a reactant, which is H plus times ClO minus over HClO. Plugging in, we have X times 0.200 molar plus X 0.140 molar minus X. This is equal to the Ka of HClO, which was 2.9 times 10 to the negative 8th. I am going to assume that the 5% rule is valid here. You could double check later, but again, since the exponent of the Ka is so small, HClO is going to dissociate very little. So then X is equal to 2.0 times 10 to the negative 7th molar. This is the concentration of H plus at equilibrium. To find pH, pH is going to be equal to negative log of H plus, which is negative log of 2.0 times 10 to the negative 7 molar. And this becomes 6.70. Here we have 40 milliliters of KOH is added. A strong base is added. We need to do a BCA table and acid-base neutralization. That means all the values must be in moles. So the first thing I'm going to do is calculate the moles of the added KOH. The moles of the hypochlorous acid is the same as before, so I'm not going to recalculate that. So starting with 40 milliliters, this is 1,000 milliliters to 1 liter, 1 liter to 0.100 moles of KOH. So we're adding 0.00400 moles of KOH. My BCA table equation is acid plus base. My acid for this equation is KClO. My base here is going to be KOH. Double replacement. So it's going to be KClO plus H2O. And we said the potassium dissociates, so this is going to be OH minus. This is going to be ClO minus. And when you even write the equation, the charges on each side must be the same because of conservation of matter. The charges, the atoms, all must be the same. So B, change in C. So the moles that I'm going to start with for the acid we calculated above is 0.00800 moles. For the OH, we just calculated right here, which is 0.00400 mole. We have none of the conjugate base, so that's 0. And the water doesn't count because it's not part of the equilibrium table. So if I look at this, my limit is going to be the base. So I'm going to subtract 0.004 moles on the reactant side. So in this problem, when I added 40 milliliters of KOH, there were 0.004 moles of KOH in the solution, which neutralized 0.004 moles of the weak acid. And on the product side, I'm going to add. Thereafter, we have to add B and change in. So this is 0.004. My OH minus is 0. And my conjugate base is a positive 0.00400 mole. Here, if you notice, the weak acid and its conjugate base are the same amount. When the moles of the conjugate pairs are equal, this is a special point. This is called midpoint. It is halfway to the equivalence point. When you are at the midpoint, you do not have to do an ice table. You could use the Henderson-Hasselbalch. So pH, remember, is negative pKa plus log of the conjugate base over the weak acid. When you are at midpoint, this becomes 0. And so pH just becomes negative pKa, which is log of the Ka. And in this case, it is 2.9 times 10 to the negative 8th. So I'm going to show you why the log cancels out. If I find the concentration of its conjugate base, moles over total volume. So the moles here is going to be 0.00400 moles divided by the total volume, which is 40 from the acid plus 40 from the base. So this becomes 1 liter over 1,000. And then the HA, which is the acid, so HClO, is also moles over total volume. This is 0.00400 moles divided by total volume, which is 40 plus 40 over 1,000 mLs. The molarity for the weak acid and the conjugate base are the same. If I have the same concentration, log of A minus, which is the conjugate base, over HA, which is the weak acid, this is log of 1. Log of 1 is equal to 0, so it cancels out. So pH is just negative log of the Ka, which is equal to 7.54. At midpoint, the moles of the weak acid and its conjugate pair, or if it's the weak base and its conjugate pair, will be the same moles. Then I would just use the Henderson-Hasselbalch because pH or pOH is going to be negative log of Ka or Kb respectively. Now 60 mLs of KOH is added. Since a strong base is added to a weak acid, the first thing we need to do is calculate the moles of KOH added to determine how much of the acid or base is neutralized. So we're going to start with what's given, which is 60 mLs of KOH. Molarity is in liters, so we need to convert milliliters into liters. There's 1,000 milliliters in 1 liter of KOH. And molarity of KOH was given as 0.1 moles per 1 liter. That becomes a conversion factor. And doing your math, you'll get 0.00600 moles of KOH. The acid that we have is going to be the same. It still is going to have 0.00800 moles because we did not add more acid. Since a strong base is added to the acid, we must write an acid-base neutralization reaction and do a before and after table to see how much of the acid or base was neutralized. So my acid is hypochlorous acid plus my base, which is potassium hydroxide. This is a double replacement reaction in which the hydrogen will replace the potassium. Potassium new partner will be hypochlorite plus water. The acid-base equation can be further simplified because anything with potassium dissociates, is soluble. So the potassium ions cancel out, so you will have hydroxide and the hypochlorite ion on the opposite side. And if you notice, my charges are balanced or conserved, and my elements and matters are also conserved. So now we start our before-after table. So before, change, and after. The number of moles of the acid is 0.00800 mole. The potassium hydroxide we calculate as 0.00600 moles. We have no ClO minus, and the water doesn't count because this is in the liquid state. Our limit is the OH minus ion, so we're going to subtract on the reactant side, and we're going to add the OH minus on the opposite side. Minus 0.00600 moles minus 0.006 0.00 moles, plus, because on the product side, it's going to appear. And after, we're going to add. So this becomes 0.00200 moles. This becomes 0. And on the product side, we have 0.00600 moles. So here the limit was the base. All the base was used up. And by the end, we only had 0.00200 moles of the acid left. Since the acid is left, we need to do an ICE table. ICE table, the calculation must be in molarity, units of molar. So it has to be moles over volume. We're going to calculate the new concentration of the acid, which is equal to the leftover moles divided by the total volume, because volume is additive, and so it will make a difference. The leftover moles are 0.00200 moles. As we calculated, that was left over after the neutralization. And my total volume is going to be 60 mLs that was added, plus the 40 mLs initially from the acid converted into liters, 0.0200 molar. So that is the new concentration of the acid. We need to repeat the procedure for its conjugate base, ClO minus. So the leftover moles here is 0.00600 moles. My total volume is still the same, 60 ml plus 40 ml converted to liters. So this is 1,000 mLs, which equals to 0.0600 molar. Now that we have the new concentration, the ICE table equation is always the weak acid being dissociated or the weak base. Since the weak acid is still present, we're just going to start with the weak acid and dissociate it. So HClO is going to dissociate into H plus ClO minus. You can also react this with water and make it into a bronzene lauric acid base. You'll get the same thing. ICE initial concentration of HClO we just calculated as 0.02 molar. The concentration of conjugate base is 0.0600 molar that we calculated, and we have no H plus ion. So the change is going to be minus X on the left side and plus X on the right side. To determine the equilibrium, I add the INC. So that's going to be 0.0200 minus X, and 0.0600 plus X. Now we go back and write our equilibrium equation. Ka, because it's an acid, is going to be products over reactants. So this is H plus ClO minus multiplied divided by the reactants, HClO. Now I'm going to plug in. So X 0.0600 plus X divided by 0.0200 minus X. The Ka was given as 2.9 times 10 to the negative 8. Since the Ka exponent is greater than 1,000th or 1,000, we could eliminate and assume the 5% rule. Plugging this in and solving for X. 9.667 times 10 to the negative 9. This is my X, or also H plus. So pH is equal to negative log of H plus, which is equal to negative log of 9.667 times 10 to the negative 9. This is equal to 8.01. The easier way to solve for this is using the Henderson-Hasselbalch equation, which is P8 is equal to pKa plus log of its conjugate base divided by the weak acid. And you have all this information. Remember, P means negative log of Ka, and Ka is given as 2.9 times 10 to the negative 8 plus log. We already calculated the concentration of the conjugate base, which was 0.0600 molar. We also calculated the weak acid, which was 0.0200 molar. And plugging it into the calculator, you should get 8.01. If you notice, they are the same answer. You could also make this a little bit simpler without even writing the ice table. So we know that concentration is moles per volume. So on top we have a moles per volume, and this is my conjugate base. And the bottom we have moles per volume, and this is my weak acid. The volume, since it's additive and they're together, are the same. So they actually simplify out. So it actually just becomes the log of the moles of the conjugate base over the moles of the weak acid. Either method works. This is a lot faster. It is up to you. Just do it correctly. Now 80 mLs of the KOH is added to the weak acid. So again, we need to figure out how much of the acid or the base is neutralized by doing an acid-base reaction and the BCA table. So calculating the moles, we have 80 milliliters of KOH converted into liters. So this is going to be 1,000 milliliters, 1 liter, and 1 liter has 0.1 mole of KOH. This equals to 0.00800 moles of KOH. So now we write an acid-base neutralization, HClO plus KOH, double replacement. So it's going to be KClO plus water. Again, the equation can be simplified because potassium becomes a spectator ion. So we have something like this: before, change, and after. Initial concentration of the acid is still the same. The calculated potassium hydroxide added is 0.008. The initial concentration of the salt is 0, and water does not count because it's liquid. Here, we notice that both the acid and base are the same moles, so there is no limit or excess. Everything is neutralized. So what that means is there is no acid, the weak acid. There is no strong base present. Only the conjugate base is present, the ClO minus. So if I do my math, this is 0. Here is 0. So all present is my conjugate. At this point, when HClO and the KOH, the two that we started with and added, are equal to 0, we are at the equivalence point. Equivalence point is the point in which the moles of the acid will equal to the moles of the base. So that means it is completely neutralized. Only the conjugate is present. In this case, it is the conjugate base. If we had a weak base and a strong acid, it would be the conjugate acid. So we cannot start the ice table equation with the weak acid. We must start it with the conjugate base here. So the conjugate base here is ClO minus. If you're having difficulty, react it with water. Then this becomes a bronze laurate acid base. ClO is the base, so it would take in a hydrogen from the water. So it will become HClO. And the water will now have one less hydrogen, so we have an OH minus. And we know this equation is correct. The charges, the element is all correct. And also, since this began with a conjugate base, I must have an OH minus on the opposite side to represent this is a basic equation. Now we have to write our ice table. So now we need to calculate the molarity of the ClO minus. So molarity of ClO minus is going to equal to moles left over divided by total volume. It's going to equal to 0.00800 moles, which is up here, divided by the total volume, which is 40 from the acid plus 80 from the base, 1 liter. This is going to equal to 0.0667 molar. So the initial concentration of the conjugate base is 0.0667 molar. Water does not count because it's in the liquid state. I have no weak acid and I have no OH minus ion. Completing the ice table is minus X plus X plus X. Equilibrium is the addition of I and C, 0.0667 minus X, X, and X. Writing the equilibrium equation is Kb, because this is a base now. Products of a reactant, so it's HClO times OH minus divided by ClO minus. Plugging in, this is X times X divided by 0.0667 minus X. But we don't know Kb. However, we could find Kb. The relationship between Kb and Ka is Kw, which is the equilibrium constant for water. This is equal to Ka times Kb. Water is 1 times 10 to the negative 14, equal to Ka, which was 2.9 times 10 to the negative 8 Kb. So Kb is equal to 3.448 times 10 to the negative 7. Plugging it in, 3.448 times 10 to the negative 7. Since my exponent for my Kb is greater than 1,000th, the x on the bottom, we could simplify that out. Solving for x, this is equal to 5.87 times 10 to the negative 4th molar, and this is my OH concentration. So now I need to solve for my POH. It's going to be negative log of OH minus. This is negative log of 5.87 times 10 to the negative 4th molar goes to 3.23, but we need to find pH, and the relationship between pH and POH is pH plus POH 14, so pH 10.77. Equivalence point. The moles of acid and the moles of the strong base added cancel each other out. They are completely neutralized. So there is no weak acid or strong base. Only thing present is this conjugate base. So when I do the ice table, I must start with the conjugate base as my reactant. If you are having difficulty writing the equation, write it as a Bronsted Lowry acid. React the conjugate base with water. Your water will behave like a Bronsted Lowry acid, and your conjugate base will react as a Bronsted Lowry base. You could solve for the Kb because the relationship between Ka times Kb is the equilibrium constant for water. Now 100 mL of the strong base is added. We know it's beyond the equivalence point because there is going to be no acid present. But we still need to figure out how much of the base is left over. So we still have to write a BCA table. Finding the moles of my strong base using dimensional analysis, still have 0.1 moles equals 0.0100 moles of KOH. We write an acid-base reaction, HClO plus KOH. Double replace it, so we're going to have KClO plus water. Before, change after. Same number of moles as before, 0.0100 moles, and then 0, and water does not count because it's in the liquid state. So we know our limit is our acid, so I'm going to subtract on the left side by the acid, and on the right side we're going to add. So after is the addition, so this is 0. This is going to be 0.002 moles, and then KClO is going to be 0.00800 mole. So if you notice, at this point, we have no weak acid, we have some conjugate base, and then we have KOH. Since KOH is a strong base, at this point, we could ignore KClO3 or ClO minus. I should have wrote this as OH minus and ClO minus. We could ignore it because it is so weak compared to OH minus. How do I know? When we calculate the Kb of ClO minus, it was 10 to the negative 7th, which is tiny compared to KOH, which is the strong base. So to find the POH, we find the concentration of the OH minus because the pH is going to be pretty much dependent on the OH minus concentration, which is the leftover moles over the total volume. This is going to equal to 0.0200 moles. Again, my volume is additive always. So this is going to be 40 milliliters from the acid, 100 milliliters from the base. This is 1,000 milliliters, 1 liter. The concentration of OH minus present is 0.014 molar. So POH is equal to negative log of OH minus, so this is negative log 0.014 molar equals to 1.85. So solving for pH plus POH equals to 14. So pH plus 1.85 equals to 14. So pH is equal to 12.15. Now we're going to sketch the titration curve. We started with 40 ml of a 0.2 molar HClO solution, which was a weak acid. A strong base of 0.1 molar was added. Initially, we had only pure weak acid. So this is when 0 ml was added of the strong base, and we got a pH of 4.12. And this is all the data points we calculated in the video. I just rewrote what their pH is when the KOH was added. This is a titration curve of a weak acid and the strong base. The volume titrant is the substance that is being added here. So here, in this case, this is potassium hydroxide. The analyte is the original solution. So in this case, that is the 8ClO. Initially, when no base was added, my pH calculator was 4.12. When 10 ml of the base was added, the pH jumped to 6.7. When 40 ml was added, the pH jumped to 7.54. When 60 ml of the base was added, pH jumped to 8.01. When 80 ml of the base was added, pH jumped to 10.77. And when 100 ml was added, pH was 12.15. So based on our calculation, we know that at 80 ml, this was our equivalence point. And therefore, at 40, we know this was our midpoint. So I'm going to draw my curve. So now we could label this. At 40, this is our midpoint when the moles of the acid and its conjugate are the same. This is also known as the half equivalence point because the volume is halfway towards the equivalence point. Right here is my equivalence point. This is when the moles of acid and base are neutralized, so there is no moles of acid or base, only the conjugate is present. And if you notice, the volume is twice the midpoint. This area right here is known as the buffering point. At this point, if you notice, the pH does not change rapidly. This is called the buffering zone. So following the Le Chatelier's principle, if there's an acid present, the base will neutralize it. If a base is present, the acid will neutralize it. This is why the pH changes very slowly. Once it reaches the equivalence point, there is no more acid or base present. Whatever the strong acid or base is present is what's going to control the pH. The equivalence point and the end point are not the same thing. The equivalence point is when the moles of acid equals the moles of base. So they are completely neutralized and not present. Only the conjugate pair is present. End point is when the indicator that you added changes color. And usually this is after the equivalence point. If it's a polyprotic acid, it will have more than one equivalence point. The key points are, if a strong acid or base is added, you must do a before and after table to figure out how many moles of the acid or base are present. Once you do that, you need to calculate the new concentration and write a bronzyloric acid base equation or dissociate your acid or base. And then you could do an ice table. A lot of the times, it's easier if you just use the Henderson-Hasselbalch equation.